Hey, I'm John Elder, and I'm doing a series on the deadly dozen data science mistakes. And today we're going to focus on mistake number 2, the focus on training too much. Now, deductive modeling, you start with a theory and you apply it to individual cases. Data science is where you go the opposite direction. It's inductively figuring out a theory from individual cases. So you start with the data, and then you build up a theory or a general rule or an equation that captures the information in the data as best you can. And that's called training. So you take the data, the dots here, they might represent a bunch of kids, and their age is the x-axis and their height is the y-axis, and you're noticing there's a trend there. And the most common way to fit data is to start with a linear regression. And so that will minimize the squared error between the line and the data points. Outliers will have a big effect, but it'll do a great job, and it's very fast and very useful. But is that the proper form of the equation? For instance, if you used a slightly more complex equation that took into account a squared term or a quadratic term, you'd probably get a better fit to the data. In fact, you're guaranteed to get at least as well and almost certainly better the more complex the model you use. So where do you stop? Because if you pushed it to the limit, if there's a distinct input value for every case, then there exists a line that will exactly fit them all. And that one's not it, but it would be crazy. It would be worse than useless in terms of predicting what really matters, which is the out of sample data, because you're using this data to build a model that will help you on new data, that will best fit the new data. So one way of handling this is to recognize that the complexity of the model needs to be penalized, just like the error needs to be penalized. And there's a whole class of formulas for doing that. Maybe the most well-known is adjusted R-squared. That takes into account the complexity of the model, the number of terms, number of features used, and penalizes that to a small extent, and you get the best trade-off. Well, it's actually in practice a very weak protection against overfit, adjusted R-squared. And there are better ones. I mentioned some of them in the blog, but the best way is probably go directly to what you're trying to do, which is minimize out-of-sample error. So use out-of-sample error in your data. Do something called resampling. Take a sample of your data, hold it out, and that'll be your evaluation data, and only train on a subset of your data. So we're representing the cases this way and the features that way. Train on one set of data and evaluate on another and give it the score. But most people stop there and do that just once. The problem is you might get lucky or unlucky in whether this data set is a valid test. You can think of this as your homework, and you're learning the material there, and then you're taking the quiz or the test. You've all experienced situations, and I know because I've been a professor before, you've all experienced situations where the test was harder than the homework suggested or way easier. You got lucky or unlucky based on the types of questions asked on the test, and that won't be a good representation of the true out-of-sample performance. So we want to use something called cross-validation. And there are other resampling methods like Bootstrap and so forth, highly recommend. But cross-validation is probably one of the most powerful and useful tools you can use in all of data science. In this case, we'll split it into 3 chunks. Some people do 10-fold cross-validation, 5-fold cross-validation. You want each chunk to be big enough to have a chance of representing your whole data set in some way, but also small enough that you can use most of the data for training. So let's break it into 3 chunks, A, B, and C. And you'll build 3 different models. The first will train on A and B and test and evaluate on C, and so forth, whereas each chunk has its one and only one time as the out-of-sample evaluation data. Now, instead of one answer for how well you did, you have 3. And I think the first time that people do this, they're pretty astonished at the variety in these answers. They're not all just 15, 15 and a half, 16. They might vary by quite a bit in terms of their answer. And before, you had taken as truth, as gospel, the one number you got, your point estimate, a statistician would call it. Now you have a distribution of numbers, and this is very valuable because you can use, in the case of just a small sample like this, the median or the mean of the distribution as your best single answer, and the spread tells you something about its it's certainty. It's uncertainty. So I'm kind of a fan of fivefold cross validation as giving you a good trade off between the size of the chunks being representative enough of the whole data set, but also giving you enough answers to provide a little distribution that will help you. And it's that value that you'll use for your evaluation of the quality of the modeling selection that you made. Now, one confusion that the next step that people have when they have started doing this is they realize they have built three completely different models, and they might have different variables they picked up on, certainly different weights, different thresholds, things like that. So what is their final model? I've got an error estimate, but an error estimate of what? Well, you have an error estimate of the modeling procedure. And to build a final model, typically people will set the hyperparameters, the guidance parameters for the model to their fixed, give them this award of result, the value, this is how well you did, but find the actual modeling parameters that will use all the data one more time to get a final fit. That's a typical thing. Now, other people sometimes use these separate models and use them as ensembles, which we'll study more in further episodes. Um, I want to leave you with two warnings before you just run off and do this willy-nilly. Number one is you want each of these chunks to be relatively uh, representative of the entire data set. So don't just take a data set and lop off one end of it or break it in the order that it's in. It's very important to randomize the cases first. So often I will create I'll store the original case number so I can get the data back to where it was for whatever, if I need to, but I'll add another column that's a random number, sort on that, and then break it into chunks so that you have a good chance of each one of them being representative. For instance, if this were kids and you had them from oldest to youngest, you'd be training on the older ones, and then you would probably do pretty poorly on predictions out of sample because the out of sample would be a very different distribution, it'd be in a very different location. So that's number one. The other caution is not every case is independent. In this example, where you have individual kids, they are. But if, let's say, this were hospital visits and so forth, you might have one patient that has multiple records. So it's important to kind of bind those together and make sure that they travel all together and a person's individual records aren't split across data sets, because then you will have a peek into the future, which is another one of the deadly dozen mistakes. You'll have some information on training about a situation that you'll later be treating as independent when it's out of sample. But unless you carry all the related records together and use them either all on training or all on out of sample, you'll be making a key mistake. So once again, to conclude, you want to fit the data well. That's very important. But a lot of times, especially new practitioners, will focus too much on getting as much possible accuracy out of it. And it's better to have a good trade-off between simplicity and accuracy, and cross-validation is one of the best ways to do that.